Good evening. My name is Jacques Booysen and I work with the Nextec group of companies. I'm a data scientist. Our specific company is named ESA, Energy Solutions and Analytics, formerly called Anyweb, and it falls in the Smart Utilities cluster of the Nextec group of companies. The Nextec group of companies does smart cities, people development solutions, domain consulting, knowledge process outsourcing, health sciences, and digital industries. But we fall in the smart utility sector. We blend engineering, business and IT capability to provide unique solutions for electrical utilities. I work in the utility analytics business areas of our company. What is data visualization? Today I'm going to give you a presentation about data visualization and typically focusing in the load research sector. In the first half of the presentation, I'm going to focus on data visualization. Why is it important? In the second half, I'll be applying it to examples in the load research sector. So here's data visualization in quotes. Visualization is the use of interactive visual representations of data to amplify cognition. The purpose of visualization is to amplify cognitive performance, not just to create interesting pictures. Information visualization should do for the mind what automobiles do for the feet. Visualization promises to help us speed our understanding and action in a world of increasing information volumes. If you just look at the world now, there's an explosion of data and the internet, specifically unstructured data. Unstructured data is data that's not in a relational database, like data from social media and Twitter. It's just growing at a tremendous rate, and to understand this data, we need to visualize it to make sense out of it. Okay, so let's talk about visualization and explanation versus exploration. There's two categories of data visualization. Basically, the exploratory side and the explanatory side. They serve two very different purposes, and you might use different tools for each one of them. So here is an example of 4 data sets that have nearly identical descriptive statistics. You see that the mean and the Pearson correlation coefficients are exactly the same, but if you visualize it, they appear to be very different. So, first scatter plot on the top left appears to be a simple linear relationship corresponding to 2 variables correlated, and it follows the assumption of normality. The points are normally distributed. The second graph is not distributed normally, but it's got the same Pearson coefficient. But you can clearly see it's not a linear relationship then. But the Pearson correlation coefficient is not applicable because it's not normally distributed. The third graph is linear, but you can see there is an outlier. So you probably need a robust regression because the regression line is not fitting the data point sufficiently. So the examples here show why data visualization is important, because the descriptive statistics give the same measures for these 4 data sets. Now we get to the process of data visualization. So let's discuss the simple process of data visualization. Firstly, we identify the business problem. Then we see the opportunity for analysis and present that to the business. Having a conversation with the business, getting a brief from the business, and looking at meeting outcomes. That's all you do before you obtain data, if it's not already in a business hub. You will have to obtain data from an external system, external provider, even social media, spreadsheets from the business. Then you'll have to identify what tools to work with to load the data and manipulate it. Then you will need to understand the data and make sure that you know what data you're looking at. You might have internal client workshops, individual and group knowledge meetings with experts in the field, look at industry benchmarks, do a peer review of your understanding of the data. And then you can get to the preparation of the data. Do your aggregation, mapping of the data, linking of the data, linking multiple data sets, and then you can plan for the delivery. Only then you start analyzing, modeling, answering questions, think about novel ways to view the answers, summary statistics, and then get to modeling and advanced analytics. And then, before you present, you need to present a narrative. That is a storyline, because it's very important to have a storyline, not just eye candy showing something beautiful by having no explanation behind it. You need to then present your assumptions that went into your modeling. You need to decide, is my visualization going to be static or is it going to be interactive? What will come out of the visualization is there any action and future plans this visualization can lead the business into next? So that is just a high-level overview of the data visualization process. So let's talk about the value of a good visualization. In this pyramid on the left, each layer forms a foundation for the next. At the bottom is the data layer, which is the raw data. Obviously, quality is very important because everything builds on top of it. So then this is an example of raw data saying red and some number. It's raw data, so we can't really interpret it. Then we add meaning to raw data. Then you apply it through the context of your problem. It could be any problem, but in this context, the traffic light I'm driving towards has turned red. And it's through the processes that you reach the wisdom that you apply an action to. Like, oh, I'd better stop my car because the robots are red. This is just a demonstration of how it works. Like I said in my last point in the slides that followed successful visualization, if we build data, information, and knowledge, and we visualize that in a successful way, then through iteration and review, this can assist in the journey to wisdom and action. Wisdom doesn't just happen, as we all know. It's often an iteration process. So what makes a good visualization? This Venn diagram shown overlaps information, story, goal, and visual form. Where they all overlap, we find successful visualization. So all four elements in this graphic are essential. With just two, you get something like a stereotypical and sketchy form, which is okay in the early stage. If you have three, then end result is strangely lacking. For example, if we combine information and visual form alone, we get eye candy or data art. If we combine information and goal and visual form without a story, it's strangely boring. It's not interesting or engaging to the audience. If we have an information and story and visual form without goal, it's useless because we're showing something pretty. It's not serving the purpose of the problem you're trying to solve or highlight it to the business. So if you have goal alone, it's just a plot. Information and a goal and a visual form is just a plot. Information and story alone is just an outline, a script or a research document. So information, story, goal, and visual form must be integrated into a good data visualization. Let's focus on the story next. Data visualizations help us by transforming complex information into something much easier to understand. Two people can interpret the same data visualization very differently. Normal visualizations tend to answer what questions, but data storytelling explains why something is happening and goes into more detail. It contributes to the visualization's interestingness, so it's not boring and engages the audience. It makes it relevant and weaves data and visualizations into a narrative tailored for a specific audience. So you need to know the audience you're presenting the data to and build your story around that. It conveys credibility in the analytical approach. It gives confidence in the results. It should give a compelling set of insights that are actionable to the audience. Now the action is very important. You mustn't leave your meeting with people having seen something pretty but not knowing what to do with it. Here I give a book reference. Visual Data Storytelling with Tableau. I found this quite an interesting book if you want to go and have a look at that. The goal is also very important. You can have data art that looks pretty, but you don't know what it is. The main goal of data visualization is to communicate information in a useful and meaningful way that's fitting, efficient, effective, elegant, accurate, and outcome-driven. It fulfills its objectives only if it encodes the given input so that your eyes can recognize and your brain can comprehend. Otherwise, it's just eye candy or data art. So what's involved to get going? There's a lot of information you can learn on the internet, and you can explore these yourself. But first, let's talk about Tableau. No programming language is required. So it's good if you're not a programmer and you know how to work Excel at least, but unfortunately it's not free. You buy a commercial software license for it. Tableau works on Mac OS and Windows. It's much like pivot tables, but much more powerful. It uses a workbook and a sheet structure, much like Microsoft Excel, but it also builds on top of that. It builds dashboards and storyboards. As we have said, stories are very important to the process of data visualization. Then some of the other stuff I'll be showing you today is in R and R Shiny. So for some of the people who don't know it, R is a language and an environment for statistical computing and graphics. R is open source and free with thousands of packages, and it can really do almost anything. To get started, you can download R and RStudio via the website links. R is really easy to download and install over the internet. RStudio is a tool and makes programming and visualization in R easy. When you start it, R creates templates for you that are already pre-populated, so you can basically modify the code, but it does involve programming. However, the programming in R is engineering programming, so it's not a lot of lines of code you have to write. You can focus on the engineering problem you want to solve. In RStudio and in R, you can do R graphics plots, you can do R Shiny, which is a very powerful open source package that provides elegant and powerful framework for building web applications in R. Now Shiny helps you turn your analysis into interactive web applications without requiring website programming knowledge. And then the third thing you can do with R is called R Markdown. It allows you to make reproducible interactive research documents. A document can be in Word, PDF based, etc. And if you produce a research report every year, you can write it in R Markdown, and every year as new data comes online or is added to your database, you can just rerun your report and it updates all the results in your template. Now, of course, you need to add the wisdom layer onto that. You can't just think that the result will be a wise reflection. It's very difficult to build wisdom into computer software at the moment. But with artificial intelligence on the rise, you never know. Machines might get more clever than us one day. So here's an example of an R plot, an exploratory data visualization. As you can see, it's literally a single line of code to plot this visualization. So there's a few datasets built into R. One of them is the iris dataset. It's for testing, and this specific dataset is from 3 species of iris flowers. Now 4 features were measured from these flowers: the length and the width of the sepals and petals. So you have 4-dimensional data, actually 5 dimensions because of the species of flower as well. So what we did here was visualize each dimension against each other dimension. In each plot, the red, green and blue indicates the flower species. In the top right hand of the plots, you can see the Pearson correlation coefficients. You can see I've drawn a wavy line to show which scatter plot relates to which correlation coefficient. It's a symmetric view that you can see. In the middle at the bottom, you can see there is a linear relationship between petal width and petal length, and you can see that there is an R-squared of 0.96. So just by using a single line of code, you can see that relationship exists, can see what's going on, and then you can move on to the modeling side, or whatever the next step will be. So the next visualization example is a visual of load classes taken from work we previously did for Eskom. The work we did here was to derive regional variants for existing national non-domestic load classes. So here we're dealing with the identification of regional, commercial, industrial and mining load classes for use in Eskom distribution network planning. The work we will show covers LPU, that's large power user customers. And the question we addressed was, how do the national load profile subclasses appear to behave differently in different regions of the country? So in theory, the differences is regional behavior, but at first we are not sure what is the regional splits and what is causing the regional behavior, and some of it is by chance. So we tested different regional spatial segmentation systems for possible spatial profile significance, finding possible spatially linked drivers. Now our final objective was to choose a regional spatial layer that mostly expresses the significant real variation in the subclass, and it will reduce the planning error when using the regional profile subclasses instead of the national version for farming of crops, for instance. So this is just some of the geospatial segmentation layers we used. We used the CSR's climatic zones as one. The dots you can see plotted are where Eskom's LPU customers, the GPS coordinates where they're sitting. The lines of dots you can see are the traction stations arranged along railway lines. These LPU customers cover all SICs, that's Standard Industrial Classification Codes. We also used several other spatial segmentation systems, including the Köppen-Geigen zones. This is a widely used classification system originated by the ancient Greeks and modified by plant specialists. It combines vegetation, temperature, and rainfall. So in this example, we've described the loads and the spatial layers. However, there were many spatial layers to choose from, and the task was to identify what layers and groupings were more appropriate to a regional classification of load behavior and at what granularity or complexity. So we tested these multiple spatial segmentation systems, each of which is a layer, and we tested all permutations and combinations of each layer. As you can see here on the bottom left, there's multiple polygons to choose from in a single layer. We isolated loads in the single polygon versus the rest of South Africa, as shown in the bottom right. The lower panel of the load profile graph shows the performance of a single polygon in a single layer against the rest of South Africa. These graphs are load shapes. They're energy normalized average winter weekday or weekend expressed per season for a single year. The solid red line shows the performance of the LPUs inside the polygon. The dotted line shows the rest of South Africa. This was a visualization to give us insight into what was happening. It didn't lead us to the end result, but it allowed us to navigate the complexity. As you can imagine, there's many combinations and permutations to test. So then we tested all the original spatial segmentation layers, and we used a trade-off technique to weigh the complexity versus accuracy using a Bayes information criteria. And as you can see by the colors in the scatter plot, each color represents a different segmentation layer. The red represents climatic zones, the black is biomes, and the blue represents the provinces. Where the BIC indicator is the lowest, that's your sweet spot, where complexity is sufficient and does not result in any greater accuracy to make further complexity worthwhile. This visualization shows that for Class 1B, that is farming of crops, 3 regional subclasses are appropriate and give us a best complexity error trade-off. 2 of the regions are in the Western Cape, and the last zone is the rest of the country. Interestingly, both the West Cape zones are in the cold and wet winter rainfall region. We haven't gone into much more detail, but clearly they use electricity very differently in their farming of crops in those 2 regions. Next, we have an example of a market intelligence tool developed in R-Shiny. The purpose of this tool was to assist planners in the network master planning process. If there was a master planning happening in a new development, planners would search the relevant piece of network by integrated media evidence to see patterns and get a more holistic view of what's going on. This tool links multiple data visualizations together in an interactive panel or dashboard. To equip this tool, we collected news articles together from SA Media, collected Twitter tweets from social media, and stored it in a NoSQL document database. The article headers are shown in the top center. The map on bottom left shows the transmission and distribution grids with the major transmission stations. The time series shows MTS hourly load profile by week, linked to the same timestamps of the news articles in the panel above. So we geocoded all the news articles and applied an XY to them. Then we applied sentiment analysis to the documents to say, was this a positive or negative document? The sentiment analysis is quite basic and we're still working on it. Certain words that appear are given scores, and the overall document is then scored positive or negative. So if I click on a document, it then zooms to the closest MTN to that document and shows the time series around the timestamp of the document. So this visualization is linking spatial and temporal information, an example of how you can and should link different views of data to obtain a holistic picture. Linked visualizations like this can be extremely effective in allowing end users to navigate masses of linked data very quickly to find out what is pertinent. This slide shows sentiment analysis. Sentiment analysis is the process of computationally identifying and categorizing opinions expressed in a piece of text, especially in order to determine whether the writer's attitude towards a particular topic, product, etc. is positive, negative, or neutral. Sentiment analysis is one way of automatically evaluating unstructured data. In this case, the topic being analyzed is Eskom, and the media is Twitter, with tweets taken between July and August 2013. This is more than 14,000 tweets referring to Eskom. The plot you're seeing is daily sentiment for each day's tweets. So here, it's hard to interpret this without a storyboard. You're seeing a graph, but what does this mean? The storyboard or narrative is very useful in transferring the meaning as shown in the next slide. You can see now we have added meaning. Here I have circled two extreme points and given a breakdown of the content or context in the points. And what we see is the positive peak on the right hand side of the graph is due to the tweets about Eskom urging customers to use less of their product. This was retweeted 64 times, and the LOL was interpreted as a positive sentiment. Inspecting the extreme low to the left, we can see two issues contributing to the sentiment score on this day. So this visualization has shown the sentiment analysis can be made more robust. Annotation in the form of a story has been used to explain this. So some of the other work we are doing in visualizing, also using R Shiny, is renewable energy forecasting models. These use historic power output, weather forecasting models, historic weather estimates. Then we have solar plant models using the location, cloud height, the cloud type, cloud masking, temperature and historic plant performance. Combined into a cloud and wind forecast model for a location, calibrated solar irradiance and wind model, calibrated plant power models to produce an hourly wind and solar generation forecast for 3 days ahead. The further you go ahead, obviously, the accuracy declines, but the main purpose was hourly IPP forecasts for 1 day ahead. Now we will go to the visualizations. This visualization that we're showing here is for IPP projects in South Africa. It's a reminder that these models use weather forecasts and satellite data to forecast in R, and then use R Shiny as the visualization tool. If you click on the IPP project Solar Capital R3, which is a 75 megawatt plant, it zooms into the aerial photo of the IPP plant, and a 6-day time series for the plant is shown. Solar irradiance forecast is shown in the blue line. The actual irradiance is shown in the orange line. You can see the actual versus forecast is rather close. It's variance day to day, but overall rather a good model. Temperature forecast versus actual is also shown. Temperature affects the efficiency of the PV plant. The temperature is also a useful forecast. So these underlying models are using advanced weather and satellite data for forecasting in R. We use R and R Shiny as a visualization tool, and this visualization shows spatial and temporal view per IPP site in South Africa. Here is another view that's also quite beautiful. It's for our concentrated solar power plants. If you select G Solar 1, we see a zoom of the G Solar 1 power plant with the characteristic tower in the middle. Also shown here is the solar irradiance and the temperature. Again, we see day-to-day variance in the predicted versus actuals, and quite close following, so obviously a reasonable model. Now here we come to the use of Tableau for visualizations. This next visualization is a result of a market analysis study to estimate the long-term energy interchanges over the interconnector between South African Power Pool and East African Power Pools in 2017. We'll now describe the background of the model that will be visualized in a bit more detail. The model that will be demonstrated estimates the least cost energy flows within and between countries in the South African Power Pool and East African Power Pool. The model is similar to the IEP for a single country extended to multiple countries. This model was developed in Message using a dynamic bottom-up multi-year energy system model applying linear and mixed integer optimization techniques, that is MILP. In this model, each country was modeled as a node interconnected with cross-border transmission lines. These models are extensive, and they include demand forecast, generation capacity, generation costs and build costs. Large amounts of data go into the model of each country, which is then cost optimized. The model estimates the within and between country energy flows, the build program and the cost for each country. This work is based on and works with the IRENA Splat model developed by Bruno Mervin of ERC at University of Cape Town, and we worked very closely with him. Parameters shown reflect features in the South African Power Pool and East African Power Pool countries' master plans of 2017. The results are shown over medium to long term up until 2040 for different scenarios. We've employed Splat model variants to conduct impact studies for cross-border transmission lines like Botswana, South Africa, Angola, Namibia, and CREDIF climate change impact studies, which we'll see visualizations of later. The result of the modeling described in the previous slide is an optimized solution for energy transfer across the region, with a detailed listing of the solution of each country and the least cost energy transfer between countries in the region. The regional solution was then visualized in Tableau. What we're showing here is a screenshot of the dashboard visualization of a regional solution shown in Tableau. The reference year for this visualization is 2025. Now on the map, bubbles show the location of generation sources by type and magnitude, and the arrows show energy interchange between countries with direction. The slider on the right-hand side of the panel controls the year displayed on the map. Bar charts on the right-hand side show energy and demand forecasts by generation source. Radio buttons on the right-hand side allows the results to be viewed with the interconnector in or out of service and allows different climate scenarios and filtering results for certain countries. This is a very dense visualization. Now, besides sheets and dashboards, Tableau also allows one to construct storyboards. A storyboard is basically like a presentation of a collection of live data visualizations with complementary annotation. The storyboard can contain pages of view windows containing one or more snapshot views of a dashboard in a particular setup. Each setup has its own zoom window and with its own control settings. Each view can have explanatory headline story text and annotation text and/or graphics. Multimedia may be included. Each storyboard can be used to communicate a narrative on the visualization of complex analysis results to the audience to enhance cognition. Let's look at a Tableau storyboard for visualization of our SAIEE model here. On the display you have a left panel consisting of two maps and a right panel consisting of one map, each with its own headline text, the narrative. Under the left narrative we have two scenarios of the model's solution shown, each with its own zoom window. The scenarios are for the year 2024 and shows the least cost energy flow for the line in and out. Under the right narrative we have a differential view showing the difference between the two scenarios in the left narrative. The right narrative has text and symbols added to give the illustration more meaning. Now this storyboard is live. One can select a different year or climatic scenario and the results change. So as an example in the slide for the reference scenario, we can see that with the connector in, we have 626 megawatt hour flow from Tanzania to Kenya. When we look at the change view on the right, we can see that adding the interconnector adds energy on the direct route and reduces the wheeling via Uganda. This solution is for free trade. It does not take the impact of bilateral agreements into account. This is a very simple view. There's a lot of dynamics happening. If you look at the dry climate, for instance, it doesn't just schedule the generators in a least cost manner, it builds the generators in a least cost manner with its lead times. The model selects between existing generation, planned generation, which is a committed build, and there's candidate generation projects, which is in the pipeline but may only be built if it's necessary to meet demand, and only in the least cost manner. Potential use cases for such modeling are impact of new generation projects or interconnectors, new generation coming online, fuel prices changing, outage analysis and contingencies, impact of renewables, average and marginal cost estimation for country under various scenarios, and CO2 emissions. Now the next visualization I'll talk about is a visualization in R-Shiny. With R-Shiny you can build rich interactive web-ready dashboards that are built of graphics, controls and code. Let's first describe the underlying model that gave rise to the data we're about to visualize. The example came from work done for Climate Resilient Infrastructure Development Fund, that is CREDIF. It asked us to model the impact of climate change electricity trade for the SADC pool over a period from 2010 to 2050. A regional planning model with multiple scenarios was constructed where the interaction between climate and load and climate and hydro generation capacity was modeled. The least cost energy transfer model was based upon IRENA-SPLAT. For this work we drew on NASA's Earth Exchange Ensemble of 21 climate change models with downscale daily data provided on a 25 kilometer square grid, so it's spatially organized. General climate change models attempt to estimate future climate for different time-based scenarios of greenhouse gases in our upper atmosphere. These scenarios are called Representative Concentration Pathways, or RCP, and the management of these RCPs is what the climate change talks seek to achieve. For each climate change model, there is also a socio-economic response model, the SSP. SSPs are scenarios of the coping of the affected economy, and hence impact on the electrical demand growth. Lastly, it was also considered important to include or exclude scenarios for the building of certain anticipated international feeders and a consideration for the openness of regional energy trading. So all of this was taken into account. This gave us more than 15,000 combinations of constraints, i.e. scenarios, of regional integrated energy plan to solve. In total then, more than 15,000 scenarios were run using Amazon High Performance Computing. This is a dashboard developed in R-Shiny to navigate the results set. Let us appreciate that we are looking at a huge amount of results here, and the results are spatial and temporal, and in some cases, i.e. for the ensemble, the results overlap. Across the top ribbon we've got controls for RCP, for economic resilience or coping, for trading, for inclusion-exclusion of international feeders, and for climate change model, of which there's 21. In the left-hand panel we have a map display showing international energy flows in the chosen year and origin of the generation in each country. On the right-hand panel we have a dual from-to interchange graphs showing energy interchange direction, each with parameter selection and display mode controls. Now just an aside, I want you to appreciate that the results of some climate models can be quite similar and there's no consensus over which is the best one. Also, there is always hope that we may still achieve a lower RCP over time. Users may therefore wish to evaluate a range of known solution risk. We therefore included a spread explorer into the graphs where specified scenario variables could be relaxed, leading to a range of results from each point in time. The spread explorer allowed the user to evaluate the min, max and mean values of results emerging from the relaxed filter conditions. This visualization is an example of how a more generic view of very specific data can be presented to usefully evaluate risk or sufficiency in a situation. In summary, we presented here a visualization of the results of an extremely complex space-time model involving interaction between climate, load, integrated regional electricity planning and econometrics, and presented the results of more than 15,000 solutions on one dash. Directed results are shown both spatially and temporally, with the ability to filter for specific results or explore the impact of a range of inputs. The results are built on data which tells the same story, achieve the goals in several ways. It's highly functional. Instead of drowning in data, we're able to understand and compare. Therefore, cognition is vastly improved. So today we've given a brief overview of data visualization. Here are some useful links for self-learning. The first half is for R and RStudio, which is free. You can download and install these yourself, as I've said. There is also a huge amount of support online and extensive add-ins developed by an expanding community. The second half is for Tableau Data Visualization Package, which is a commercial offering. You can buy a license to create, i.e. author content in Tableau. However, your visualizations or storyboards do not require license for viewing by the client with its reader application. Both these packages contain many embedded examples. This makes it very easy to send a dash or storyboard or sheet to a client who can then browse the result and work the controls. If you have any questions, please feel free to contact us at the details given in this presentation. We hope you find this as interesting as we do. Thanks for watching. Goodbye.